while I get my laptop set up. So when I was preparing this talk, I've got a folder on my hard drive that has talks related to Jupyter and Ipython. And actually, it had a folder for SciPy 2006. That was my first talk at SciPy. Obviously, it was a much smaller conference at the time. It was at Caltech. And one thing that I was reminiscing about and have talked with Eric about is today, I think it's pretty obvious that all of us here think it's reasonable and rational to use open source software for scientific computing. That was not the case in 2006. All of us who were there, I think, had the sense that there was something exciting about what was going on. At the same time, we spent a lot of time looking at each other saying, we're not crazy, right? And the other person would say, yeah, we're not crazy. We're not crazy. And that actually continued on for a good part of a decade, believe it or not. I think it was sometime, in my mind, around 2010, 2011, that the tide really started to shift in a broad way where people started to take it for granted that, oh, of course you would use open source software for things like this. And part of what I really like about the SciPy conference, let's get, oh my goodness, that's small. Let's see, 1080, much better. And I'm mirroring. One of the things that I appreciate about the SciPy conference is it's been going for a long time, and there's a really strong sense of family here. For those of you who are new, I hope that's something you experience while you're here. A lot of us, when Eric and I were talking a few days ago, we said it really feels like a family. There's people here that we've been seeing for over a decade, not just at this conference, but other conferences. A great example of that is Min, one of the core developers to Ipython back in the early 2000s, was a student of mine at Santa Clara University at the time. And so there's a lot of long histories here in the room, and it's great to be back. So I want to start out talking about Jupyter, and I've got a BuzzFeed-style listicle, some slides on Jupyter titled 8 Awesome Things About Project Jupyter You Don't Want to Miss. So the first, Ipython 5.0. In the last few weeks, we've released Ipython 5.0. For those of you who aren't familiar with the old school classic Ipython, it's a terminal-based user interface to the Jupyter ecosystem. And a lot of work has been put into that classic terminal interface. There's better multi-line editing, syntax highlighting, improved tab completion, and a lot of other features. It's really a fantastic user interface if you're still working at the terminal. It is the last Ipython release to support Python 2. So this is yes, definitely, that's worth giving an applause for. It's the first of our projects to make this transition. We're really excited about it, and we're hoping to sort of help lead the community through this transition of dropping Python 2 support and moving towards Python 3. There's a very nice blog post here about sort of the transition to Python 3, what that will mean, how that will happen. Next, I want to highlight a couple of talks related to Jupyter here at SciPy 2016. First is NBFlow. This will be by Jess Hamrick later today, reproducible one-button workflows with the Jupyter Notebook and sconnes. For those of you who are managing complex workflows that involve Jupyter Notebooks, I highly encourage you to attend that talk. Tomorrow evening, we're going to be showing for the first time in a public context the next generation user interface for Project Jupyter. This is called Jupyter Lab, and I'll be giving this talk with Jason Grout. So Jupyter Lab, building blocks for interactive computing. There's a large group of people who have been working on this as part of the project, and we're really excited to show this to you for the first time publicly. On Friday, Min Reagan Kelly is going to be talking about some work that he and others have been doing to relieve one of the main pain points that you likely have in working with notebooks, namely how do you version control them, and the difficulty of diffing and merging notebooks, their JSON data under on the file system, And so here's a small screenshot of a library called NBDime that they've written that can actually diff and merge notebooks in a semantically meaningful way, do things like ignore output when you're diffing and merging. So please come to that. We're really excited about that work. Jupyter Hub. Jupyter Hub is our multi-user version of the Jupyter Notebook. And Michael Milligan is going to be giving a talk shortly after this entitled Jupyter Hub, misspelled Jupyter Hub there, as an interactive supercomputing gateway, talking about how Jupyter Hub is rapidly becoming a user interface for exposing supercomputers to users. Traditionally, if you've ever used a supercomputer, the, quote, user interface was SSH. Which is quite painful, and so we're really excited to see Jupyter Hub being embraced in that community. Next, user testing. As part of our work on Jupyter Lab, we are going to be performing in-person user testing here at SciPy. This would take 30 minutes of your time. It's one-on-one user testing. You get a Jupyter t-shirt out of this. We've got brand new Jupyter t-shirts. Sylvan, want to stand up and show everyone the new Jupyter t-shirts? So you'll get a new Jupyter t-shirt. Thank you, Sylvan. And help us improve the user experience of Jupyter Lab. If you want to sign up for that, we have a few spots left. There's a bit.ly link here, bit.ly Jupyter user testing. In particular, if you're a new user to Jupyter, or even if you've never used Jupyter before, please sign up. That's a particular sort of segment that we really want to user test well. And right now, I think we have a lot of people who are signed up who are more experienced Jupyter users, so that would help us a lot. Next, Jupyter Steering Council. We're pleased to announce a new Steering Council member in 2016, Sylvan Corlay, who just modeled the new Jupyter t-shirt. Let's give Sylvan a hand. Sylvan has been a core contributor to the Ipython widgets, is one of the lead authors of BQplot, a plotting library based on the Ipython widgets. He's made contributions to the IPy leaflet library, and then has done a lot of work with us on the new Jupyter Lab work and the existing notebook. So we're really pleased to have him as a steering council member. Sylvan joins the other steering council members listed here. Those who are shown in italics here are actually at the conference. So if you want to find people who are working on Jupyter, these are some of the people who are here. We also have 8 Cal Poly students who are here at SciPy the first time this year, and they are all working on Jupyter Lab, so you'll see them around as well. We have a new Jupyter newsletter that we've rolled out in the last few months. We're publishing that on Medium. If you go to newsletter.jupyter.org, you can read it there on Medium, or you can actually subscribe and have it sent to your email inbox every month. We are at Project Jupyter on Twitter. We encourage you to follow us there. That's one of the main places that we sort of disseminate news about the project. One exciting thing that's coming up is JupyterCon 2016. You may have seen over the last year that we've started smaller one-day conferences called Jupyter Days. We've had Jupyter Days in a number of locations around the country. There's others in planning. JupyterCon will be a larger multi-day conference in the Bay Area this December. So please watch our Twitter channel, our mailing list for details about that. All right, so that's it. What I'd like to do now is switch gears a bit and talk about a new project, a new piece of software that's been released in the last week. I think everyone's really excited about it. No, I'm not talking about Pokemon Go. So for the last 9 months, a few of us have been talking about statistical visualization in Python. And a lot of these conversations have been with the core contributors to existing visualization libraries, such as Matplotlib, Bokeh, Plotly. And Jake Vanderplas and I have spent a lot of time on this, and we're really pleased today to announce a new statistical visualization library for Python. It was just released on Monday, so this was all the code that we were writing this weekend. And so I want to talk to you about Altair today. So visualization in Python, there's a lot of power. There are many existing libraries for visualization in Python. Matplotlib, Seaborn, Plotly, Bokeh, Lightning, Pandas has built-in plotting. There's a lot of other plotting libraries as well. And each of these plotting libraries does something really well, does many things really well. And I guess the way that I think about it is at this point, there's really not any visualization that you would want to make that you couldn't make in Python. And it's a really fantastic situation from that perspective. Furthermore, many of these plotting APIs have fairly solid theoretical underpinnings. A lot of us are fond of Wilkinson's grammar of graphics, and I know that's influenced a lot of these libraries. On the other hand, there's a lot of pain still in the visualization space in Python. It's one of the most persistent and significant sources of pain that we hear from users. We hear things like, I've been using Matplotlib for a decade now, and I still have to look most things up. I love Python, but when I do visualization, I switch over to R and use ggplot2. Why is that the case? A couple of things. One, there's a very sparse handling of statistical visualization, and in particular, categorical data and date-time data in these different libraries. Users have to write code, even for incidental aspects of the visualizations. And new and experienced users have to track and learn all these given libraries and make decisions about what library to use for a given task. It's not uncommon when we sort of are working with users and see people, it's not like they can pick one visualization library and stick with it. They're going to start with Matplotlib and then realize, oh, well, I want this theming from Seaborn. But then they're working in Seaborn and they realize that they've got to jump over to Plotly because they want interactivity, or Bokeh because they want interactivity. That's really, really painful. All of these APIs are massive, and so it's very burdensome for users to track all of this. And many of the most basic things are still fairly complicated in these libraries. So just an example. I'm not advising you try this at home. You may have done things like this yourself to sort of show the pain involved with this. So if you fire up the Jupyter Notebook sometime, import Matplotlib or your favorite library, grab a data frame of your choice from Pandas, make a 2D scatter plot using 2 quantitative columns. For that, you would probably start out using Matplotlib plt.scatter, right? Fairly simple. Now facet your scatter plot by a categorical column. So you've got a couple options. You could use Matplotlib's built-in subfigures. You could hop over to Seaborn and use facet grid. It's possible, I think actually Pandas has some faceting built in, so maybe you could use that. Now try faceted histograms or bar charts. One of the things that's fantastic about this is faceting support is not uniform in these libraries across the different chart types. So Pandas may have faceted scatter plots. At one point, it didn't have faceted histograms. Maybe it does today. I can't keep track. Then try coloring pointer bars by the hour of a date-time column. This one would be particularly fun. Pandas probably would be your best bet, but you very well may need to start doing group bys yourself and using something like subfigures and facet grids. Now try teaching this to someone who's learning data science or scientific computing, or trying to convince an R user that Python is really cool. There's a lot of pain here. What do I mean by statistical visualization, right? This is very different from visualization as a whole. Here's my take on it. First, the data to be visualized, the source is a data frame. So this is a very constrained model. It does not include, for example, 2-dimensional arrays of data or 3-dimensional or higher dimensional cubes of data. So things like contour plots or 3D scatter plots are completely off the table, right? So it's a constrained model of the data. Furthermore, the data frame is in a tidy format. The tidy format, that phrase comes from Hadley Wickham. He has a very nice paper. It's linked to here. And the short take on that is that the columns of the data frame are observed variables of a given type, either quantitative, categorical, or date time. The rows are samples, and that's a rough idea of what the tidy data format is. Furthermore, the data is mapped to visual properties such as X position, Y position, color, shape, faceting, using group by operations. So pandas and SQL have a group by operation that basically allows you to split the rows of your data frame into different groups based on the value of a particular column or columns. And these groups, from a theoretical perspective, correspond to conditional probability distributions. For the most part, that doesn't really matter from a practical perspective. But this idea of using group by operations to map data to visual properties is really at the heart of statistical visualization. So one of the ideas that's important in this field is that of a visualization grammar. And as a theoretical physicist, having clean abstractions has always been really important. If you think about something like Newton's laws, with a few number of abstractions, F equals ma, the idea that the state of a system is represented by a vector in some vector space, and that you could actually observe that vector in real systems, and that you can model that vector using by solving Newton's third law, F equals ma, is a very powerful idea, and those few abstractions can be reused across a wide range of contexts. That's really what a visualization grammar gives you. It gives you a few number of abstractions that you can use to build very complex visualizations. The first layer is the data. You want to send the data into the visualization. Next, the data gets transformed. This is something that I hadn't appreciated fully, that for a visualization grammar to be powerful and effective, you really need to include the transformations within the visualization context. This is very different from, I think, the traditional thinking, where the idea is you transform it first, get it into a state, and then you visualize it. In statistical visualization, it's really important to include those transformations, the group bys, the aggregation, statistics, projections, layouts. Next, you need to map the data, the transformed data, onto visual properties. That's really what a scale does. So for example, you need to know how to map a second from a date time column onto a color, right? That's something that you have to actually tell how that should be done, and a scale is an object that does that. Next, you need to map scales onto basically visualized scales. Typically that's done by the axes of a plot. A legend is another example of a visualization of a categorical scale. And then lastly, you need to map the data onto marks, so points or bars or lines. The other idea that's critical in Altair is that it is a declarative API, or a declarative language. And I would like to contrast a declarative approach with an imperative approach. So first, in a declarative approach, you specify what should be done instead of how it should be done in the imperative approach. And the important part of that is that how something is done in a declarative context is completely an implementation detail that a user should never, ever have to know about. It's really up to the implementer of that declarative API to decide how something should be done. And it really separates the execution of what should be done from the specification of what should be done. In the imperative approach, you must provide detailed logic and steps for how everything should be done. This gets difficult because if the what ever changes in an imperative approach, the steps and logic could change significantly. Whereas in a declarative approach, you can hide those changes in the steps and the logic from the user. So why a declarative API? First and foremost, usability. The what question is usually closer to the user's end goal than the how question. Most often, users don't really care how something gets done. They're trying to get something done related to the data set they're working with, and they would be completely fine if there was a magic genie that could come and give them what they want, right? A lot of us love to write code, but when we're working with data, writing code can actually get in the way of us understanding the data. Second, declarative approaches usually lead to users writing less code. They don't have to give all the steps. They can simply say what needs to be done, and the magic genie will produce it. Furthermore, there's typically fewer abstractions, so there's a smaller, lower cognitive load on the user trying to understand those APIs. There's a lot of practical effects for declarative API. One is that there's a natural serialization format. In the visualization space, declarative APIs are easily mapped onto JSON data structures, which can be put on a file system, can be sent over the network. It's also possible to auto-generate code from these JSON structures, and that's something I'll talk about more in a second here. This makes it easier to support multiple languages. It's not a coincidence that some of the more modern visualization libraries, such as Bokeh and Plotly, have declarative JSON data structures underneath, and it's been much easier for them to support other programming languages other than Python. And then last is performance. In an imperative approach, it's very easy to write code that may be horrifically slow. In a declarative approach, the library author can basically be responsible for that. A user doesn't have to be responsible for the performance optimizations. Obviously, there's no guarantee that the author of that library will be successful, but at least there's the chance for the author to do that without the user needing to worry about that. So you might be thinking, oh no, not another visualization library. Where does this fit in? There's obviously a lot out there already. And so I sort of want to map out the existing space of a few of these existing libraries across the different axes here. Ease of use, so sort of high level, some of the statistical visualization versus lower level, very powerful, and then imperative versus declarative. Matplotlib is a canonical, very, very powerful, but imperative plotting library. There's really not anything you can't do with Matplotlib, and that's part of what has made it so extremely popular. Seaborn offers a lot of the statistical visualization, but it's still, for the most part, imperative. If you want faceting in Seaborn, you have to write, in many cases, a for loop and actually iterate over the subplots and call individual plotting functions on that. On the powerful but declarative side, there's libraries like D3 and Vega, but then also Bokeh and Plotly. And then for the statistical visualization on the declarative side, there's ggplot2, which started in R. There is a Python implementation of that. Vega-Lite, which I'll be talking about in a second. And then also some of the high-level charting in Bokeh I would put into this category, being sort of statistical visualization, but still declarative. So a bit more about declarative visualization and the state of the art in that. One really important library that has come on the scene in the last decade is D3.js. A lot of you have probably heard about this. Came out of the group of Jeff Here. He was at Stanford at the time, and Mike Bostock was a student of Jeff Here. Jeff is now at the University of Washington as a faculty member there. And D3 is a JavaScript library. It's mostly a declarative language. Sometimes you end up writing callbacks, so there's a little bit of imperative aspects mixed in there. It's extremely powerful, but very verbose. So here's a simple example of a bar chart done in D3.js. And it's pretty clear that if you were a user trying to get a data visualization done, D3 probably wouldn't be your first choice unless this was a sort of a custom bespoke graphic for a one-off type situation where you really had the time to put in. So it's low level, but it is declarative. On top of that is Vega. My take on Vega is that it's basically making D3 a declarative JSON data structure. And so here's the same chart or a similar chart done in Vega. So the source for a Vega visualization is a JSON structure, and then there's a JSON library, a JavaScript library, which compiles that JSON down to D3 JavaScript code. Again, very powerful, but fairly verbose. If you want to sort of compare this to libraries in the Python space, I think Vega is very similar to the lower level parts of Bokeh and Plotly. The JSON and actually BQ-plot, I think there's a lot of similarities at this level as well. And then at the highest level is sort of the statistical visualization. And Vega-Lite is a new JSON specification. All three, D3, Vega, and Vega-Lite, have come out of Jeff Here's Interactive Data Lab at the University of Washington. And Vega-Lite has come out, the 1.0 came out in the last 6 months. It's, again, a JSON specification, and then there's an accompanying JavaScript library that compiles Vega-Lite down to Vega, and then Vega gets compiled down into D3 for rendering. And so you can see here is the JSON specification for Vega-Lite for a bar chart. Much more concise. And here you're really focused on the highest level details that a user would care about. So for example, here you've got data. You're going to have a mark type of a bar. And then the X position is going to be column A, the Y position column B. A is an ordinal, which is an ordered categorical, and then B is a quantitative column, basically a number. So much more concise. And this is really the layer here, the Vega-Lite layer, where we want to target, and that users really want to be interacting with their data. It's comparable to ggplot2, if you think about other sort of high-level statistical visualization libraries. Other things about Vega-Lite, very important, it's a constrained visualization model. Again, it falls under this category of statistical visualization. You're not going to see it working with two-dimensional arrays of data or higher dimensional data. And it really embraces this group by operation. I'll talk more about that. There's an online Vega-Lite editor. I can show that later if I have time. And then there's even, Jeff here has also built a Tableau-style user interface on top of Vega-Lite as well called Polestar. One of the things that's fantastic about the declarative approach is it's very easy to build layers on top of that. For example, like a full-blown user interface where a user doesn't have to write any code at all. So how does Altair fit into this? So Altair is a Python API for declarative statistical visualizations. This is something that Jake and I have been working on in sort of getting the 1.0 release over the last few months. It's important that Altair is not really another visualization library in that it does not do any rendering, and it also, basically all it does is emit type-checked and validated JSON data structures that follow the Vega-Lite specification. So it's a very simple Python library in many respects, and we're really delegating, honestly, all of the hard work to Vega-Lite and other renderers that could potentially render that Vega-Lite spec. We currently ship a default render that will use the sort of the canonical reference implementation, the JavaScript render for Vega-Lite that Jeff here's group has developed, and that works in the Jupyter notebook. We've been talking to the developers of Matplotlib, Plotly, and Bokeh. There's strong interest from them for them to implement their own Vega-Lite renders. Part of what we saw on the horizon as people were becoming aware of statistical visualization in Python was, honestly, we were worried that all of these libraries would go implement their own statistical visualization APIs. And from a user's perspective, I think that really would hurt the community because really, quite honestly, users don't need 10 libraries that do something. They need one thing that does it really well. So we're hoping that Vega-Lite and Altair from the Python side can become really a sort of a lingua franca of statistical visualization in Python. And so we're excited that these other plotting libraries are interested in rendering Vega-Lite. One thing that's important about this is that each of the different renderers from this perspective have strengths. For example, if you want publication-ready, pixel-perfect, vector-drawn PDFs, you're probably going to want to use Matplotlib. And so it's really important that Matplotlib can integrate with these statistical visualization layers. If you want high levels of interactivity with tooltips and panning and zooming in the browser, Bokeh and Plotly or BQplot are fantastic examples of libraries that you would want to render the Vega-Lite spec. And so from our perspective, we really think that users should have a choice from the rendering perspective. That doesn't mean they should have sort of cornucopia of APIs to sort through to get the visualizations done. So what does it look like? Here's a simple Altair visualization. We ship with around 40 different example data sets. And so here's the cars data set. The first thing you do is you create a chart passing your data. The data in this case, again, is a pandas data frame. Then you pick a mark, in this case circles, and then you call the encode method. And the word encode here is a shorthand for visual encoding. And the way to think about this is visual encoding is a process of associating data and mapping that data onto some visual property. So in this case, we are mapping the horsepower column, that's just the string name of a column in the data frame, to the X position, the miles per gallon column to the Y position, and the color to the origin. All the internal details are taken care of by Altair in terms of producing the JSON spec and then passing it off to Vega-Lite, which gets compiled to Vega, which gets rendered using D3. The group by operation is implicit here. So again, this is declarative. The user doesn't have to actually explicitly say, I want to group my data frame by the origin column and then pick a different color for each of the different origins in that process. Also notice that things like the legends are automatically labeled, and also the X and Y axes are automatically labeled. You can obviously customize them, but again, very few lines of code to get a visualization. So Altair is robust. It's been really fun to work on this. Most of the code in the Altair code base is auto-generated from the Vega-Lite specification. All the core internal API is auto-generated. Our tests are auto-generated. Our example notebooks are auto-generated. This is really important because the Vega-Lite spec is still evolving. And this allows us basically to ensure that for any given release of Vega-Lite, that we're following that specification as precisely as the JSON specification that they've produced. Obviously, if they have bugs in that JSON specification, we will faithfully reproduce those bugs. Altair performs type checking and validation using the traitlets library that's come out of the Ipython Jupyter ecosystem. What this means is the JSON data, the visualization that's produced by Altair, is essentially guaranteed to be valid Vega-Lite. That doesn't mean it's going to produce the visualization you want, but at least it's going to be valid JSON from the Vega-Lite perspective. Altair is usable. Jake and I have spent a lot of time focusing on the usability of the API. This is really, in our minds, what makes the biggest difference. Quite honestly, from the technical perspective, any of you could just sit down and write raw JSON data and pass it to the Vega-Lite. There's a Python library that can render Vega-Lite JSON, and that would give you the same visualizations. From an API perspective, though, that's really painful to write that by hand. So what do we provide from the usability perspective? Type-checked attributes. There's a thin layer, so it's mostly an attribute-oriented API. There's a thin layer of convenience methods, not many. And then there's nice features such as method chaining and a sort of a sparse choice of operator overloads for like plus and plus equals for layering. We can also provide intelligent heuristics, such as type inference to reduce the amount of code needed. So we can do things like infer that this column is a date-time column or infer that it's a categorical column. We've also provided a shorthand notation for specifying the names of columns, data types, and aggregations. And then one thing that we faced is that the JSON spec for Vega-Lite is fairly nested. And we're trying to embrace one of the sort of Python ideas that flat is better than nested. And so we've sort of very carefully made API choices to flatten that API while staying true to the underlying Vega-Lite spec. And I think we're really excited about that aspect of it. And there's extensive documentation and over 70 examples that are included with Altair. So Altair is powerful. You can render Altair in the Jupyter notebook. The default is Canvas or SVG. The underlying Vega renderer can be configured to use both. I think right now the default is Canvas. When you use it in the Jupyter Notebook, PNGs are also saved anytime you do visualization. So if you upload your notebook to GitHub, the visualizations will still show, which is really important. Obviously, they'll also be visible on MB Viewer. You'll see here shortly that all the visualizations in the notebook have a link to download a PNG or to view in the online Vega-Lite editor that Jeff Heer's group provides. You can obviously easily serialize these visualizations to JSON files. We also have the ability to auto-produce a standalone HTML page that has these visualizations. And then you can even invert the process. So if you find a visualization on the internet somewhere that's the Vega-Lite JSON, you can copy and paste that into a Jupyter Notebook, and Altair can automatically generate the Python code using the Altair API that would produce that visualization from the Python perspective. Honestly, all these things were fairly easy to do given the decorative nature of Vega-Lite. It really gives us sort of superpowers, and so it's been really fun to do this. So what I'd like to do now is spend a little bit of time exploring Altair in a live demo. You can install it yourself at this point. The conda install here line is here. You can pip install Altair. If you use pip, you do have to use Jupyter NB extension install to install the JavaScript code associated with this. The conda package does that automatically. And then Altair comes with a set of tutorial notebooks. And so if you do from Altair import star and then call the tutorial function, that will grab the tutorial notebooks and put them in your current working directory for you to explore. If you don't want to follow along in live notebooks, if you click, just go to the Altair website. Right here, there's the Altair documentation. These are just the Jupyter notebooks associated with that, and you can read them on GitHub. So let's go over here. I realize I am getting close to the end. So this is what your notebook would look like after you call the tutorial function. I'm going to hop into the introduction notebook here. And so I want to start to walk you through the API here very briefly. So again, the first thing you start with is the data. In this case, we're going to start with a simple pandas data frame. Make it a little bit bigger. And then the next thing is to create a chart. All you're going to do is pass the data to the chart. Notice in this case, it's using all the defaults. All the data gets mapped onto a circle, and I've not done any of the visual encoding. And so at this point, let's actually look at the JSON data that's produced by this. We see at this point there's a values field that has the actual data, and then the mark has been set to point. Usually, rather than using the default mark type, you'll want to specify the mark explicitly using methods such as mark_point. Next is the visual encoding. Let's toggle the header. The visual properties that Altair and Vega-Lite support are X, Y, color, opacity, shape, size, row, column for faceting and trellis plots, detailed text, label, path, and order. So there's a very rich set of visual properties. So for example, let's use a point mark and then encode the A column using the Y position. Right? So in this case, Altair is smart enough to know that A is a categorical column, so it uses a categorical axis. And you can see that we've got a fairly simple visualization. Let's look at the JSON data. And at this point, we see there's a new encoding field in the JSON data structure. The Y column field is simply the name of the column. You can see A here is one of the columns in the data, and the type is nominal. Altair and Vega-Lite support two categorical data types, ordinal and nominal. Ordinal is a sorted or an ordered categorical type, and nominal is an unordered categorical type. There are 4 basic data types supported by Vega-Lite and Altair. Those are listed here: quantitative, nominal, ordinal, and temporal. They each have a 1-letter code, Q, N, O, and T. And you can actually, so we in Altair will try to infer the data type automatically if we get it wrong. For example, you often have to specify explicitly if you want to use ordinal or nominal. You can simply do that by postfixing the column name with a colon and then a capital letter indicating the data type. So in this case, I'm switching to encoding column A using the X position, and then I'm just saying I want that to be an ordinal data type. You can add other columns simply by listing them as additional keyword arguments. So in this case, I'm going to say the X position is B, the Y position is column A. Again, the entire architecture is smart enough here to know that B is a quantitative column and A is a categorical column. If I want to make a bar chart, all I have to do at this point is switch the mark method. And this is one thing that's really powerful about Vega-Lite and Altair, is that basically any of the visual encodings can be used with any of the mark types. They're fully exchangeable. Doesn't mean you're always going to get a visualization that makes sense. Some mark types are more appropriate for some types of visual encodings, but there's a lot of flexibility there. Notice I've also switched to a slightly different syntax here. So above I was saying X equals string B, the column name. You can also pass positional arguments, and we provide in Altair objects named X, Y, row, column. And the benefit there is that you can provide additional keyword arguments to those objects that configure how those objects will function. So for example, you could set a log scale on the X encoding, for example. The different marks that are supported are listed here: area, bar, circle, line, point, rule, square, text, and tick. The next is aggregation. And so the shorthand notation that we've introduced is that when you're specifying the name of the column, you can provide basically a function syntax. So here we're going to take the average of the B column grouped by the A values, right? And so here's where you're combining aggregation and grouping, right? So underneath the hood, this would look something like the following pandas call. You're doing a group by on column A and then calling the mean, right? And so again, it's really important to include the transformations in the visualization grammar. Here, we can simply, typically, if you're going to aggregate like this, you might want to use a bar chart. And so here is a bar chart where we're taking the average of B grouped by A. And again, you can look at the JSON data for this time omitting the data. And you can see the aggregation is specified by an aggregate field in the JSON data structure. Again, the underlying JSON structure is really, really simple. Okay. So at this point, I've got 2 or 3 minutes. I want to show you some other visualizations. Actually, let me jump ahead. So one thing that Altair and Vega-Lite now have is layering. And so the idea of layering is being able to pick multiple mark types in a single chart or even subchart. And one of the ways you can use that is using regression plots. And so this is an example. So what we have here is a very simple data set, X and Y position. So we're going to form basically a scatter plot and then perform regression on that scatter plot, and then a categorical column here. And I'm not going to go into the detail here, but we have subclass chart. And what this subclass does is it takes a simple regression model and then performs all of the group by operations that are implicit in the visualization and does the regression on the individual groups, right? And so here's a simple example of doing a chart and doing the regression globally. So we're going to use all the rows in that data frame, do a regression on those, completely ignoring that categorical column. If, however, we say that we want to map the color to that categorical column, the regression plot will automatically respect that grouping, right? And this grouping will work across any of the different visual properties that Altair and Vega-Lite support. So you could say, I want to encode column C as the shape, or I want to encode it using rows or columns of a facet, something like that. Another example is it's really simple to pass a different function, a different model to use for the regression. So here's a cubic regression example. And again, so we're doing the grouping underneath the hood, the regression model on top of that. And again, Altair has no built-in regression capabilities. All this could be done with a fairly simple, I'll put that in quote, subclass of the chart object. Again, want to emphasize we have a fairly rich tutorial here. And then in the, let's see here, let me show you one other thing. So if I click on Altair tutorial, in the auto examples, here are 70 different examples that we auto-generate from the Vega-Lite code base. So just about every feature that Vega-Lite supports, we have an actual Jupyter notebook to support. We encourage you to drop by GitHub, and let me finish up giving some thanks here. There's the GitHub repository. Special thanks to Jeff here and members of his group at the University of Washington, in particular Dominique and Arvind, who are some of the core contributors on the underlying libraries. Furthermore, if you're an R, Julia, Scala developer interested in creating an Altair implementation for your language, please get in touch. Most of the hard work is done. And what I mean by that is Altair has Python packages for auto-generating Vega-Lite-based APIs in different languages. And so really all you have to do is overwrite those Jinja templates, and you've got an Altair API for another language. Thanks a lot. So the question was, there's no examples of in the Altair examples or documentation that have error bars. So this is one of the disadvantages of this approach is that it is highly constrained. And the constraints primarily are that we're subject to, at this point, the constraints of Vega-Lite and Vega. Vega is very general and could easily render error bars. They've not implemented that in Vega-Lite. Part of what we're hoping to do is to dramatically expand the effective user base of Vega-Lite, and then work with Jeff here's group to basically ask him, okay, so we're hearing from users that error bars are really important. How do we encode those? My guess is error bars are a strong possibility. There's other things that we are aware that are on the roadmap, such as handling geodata. That would be another core data type that obviously you would want to be able to express in this context. But basically, come to Altair, open an issue, and we'll have those discussions with Jeff here's group. One more question. Yeah?
Is it possible to take the result and grab it to implement those things, not implement, but to create those things yourself?
Can you clarify a little bit? So
once you produce the chart, if you go over to the Vega editor or some other editor, can you get down to a level where you could do an error bar?
So you can, that's a great question. I think you probably could. So you can so if you open one of these visualizations in the online Vega-Lite editor, you can view the compiled Vega representation, copy and paste that, and then start to modify it. And Vega itself is extremely powerful. Another thing that's on the roadmap, Vega has implemented a declarative approach for interactivity, panning, zooming, selections, and they're currently working on how to expose that up at the higher level of Vega-Lite. So that eventually will show up as well. I think we should stop there. Thanks a lot. And so myself, I will be at the sprints, willing to talk to people about Altair, and then the much larger Jupyter team will also be at the sprints. Please stop by. Would love to hack with you all. Thanks.